you also want to try?
No, I'm fine.
Okay, then let's go on. So I will give first a few points about what Rust brings to developer. So you probably already heard about ownership and movement semantics in Rust, where you basically have, it's also called defined types if you're coming from a functional programming background. You can basically use an object only once somewhere or not at all. And if you use it once, then it's basically gone. So there would be a move. And there are also borrowing rules, which basically means if you want to create a reference, you can create infinite many immutable reference or just one mutable reference. And they kind of constrain basically eliminates a lot of issues you have for dangling pointers, and also eliminates a lot of racing conditions you can generate for your program. The second one is pattern matching. So Rust also has some types, which basically allows you to encode like state machines. It's basically like a closed set where you just enumerate all your variants. And it's like a union, but you can also have elements for each variant of your union. And then you can pattern match on them, which is very helpful, for example, to encode like AST, any language you want. And also, like I said, if you want to encode some state machine, it's helpful. What I also want to touch is so-called ad hoc polymorphism. So this is also coming from a functional programming background. In Haskell, they call it like type classes, or for example, in C#, it's more like interfaces. You can basically implement in Rust, they call trait, a functionality for a certain object. And when you do this, you can use this in so-called compile time generics. So this is a function which takes like a at compile time generic parameter I. It's an iterator of 32 bits floats and returns to some, I don't know. The important thing is if you call it now with two different types, so the first one would be like over integers and the second over floats. What Rust does, it's called monomorphization. It's basically at compile time fills out this constraint and makes two concrete implementations of this and compiles them separately, which increases binary sizes, but also allows like the type is very concrete, and this is also helpful for Enzyme. And this is the point where we come later on, where we integrate Enzyme into the compilation process. And also we have like excellent tooling, so Rust is very well known for its cargo build system and also for its community. All right, okay. So we will now talk a bit about prior approaches.
Okay, yes. So now that we know why we want to experiment a bit with Rust, and we probably are here for Enzyme, so we are curious how we can integrate those tools. And well, there have been quite a few approaches. The first one around 2020 from another member of our Rust ML community, which was quite interesting because, well, he used Clang and basically copied the whole C++ setup which we had in an earlier talk. So he defined our __ enzyme autodiff functions. He used those magic numbers to encode basically what we know as enzyme const, enzyme duplicated, and so on. And he did some basic debug information in parsing so that he could basically use the Rust compiler only to compile all our Rust source code into LVMIR, and from there on move on with opt, Clang, and the enzyme parse, which we already use on the C++ side. That was nice because it showed us that we generally can use enzyme on the Rust side, but it had quite a few limitations, like only being able to use a single Rust crate, or what you might know as a repository, so dependencies didn't really work. You were not really able to use Rust types because most of them don't show up in the debug information, and you don't want to write a Rust program just using C types, which have a defined layout. So it was a starting point on which we iterated later on. The next iteration is here using build script. So, well, since we want to use the grades.io ecosystem for a lot of dependencies, I thought it might be wise to just integrate into the build system called Cargo. The approach which we took is compile all your Rust source code, all your dependencies, again, into LVM bitcode. Now that you use Cargo, it's going to be a huge bitcode file, but I mean, that's, well, one of the issues of the approach we had. You can then pass all of that to Enzyme. Now, instead of using the enzyme parse, you use the API, which gives a lot of control. Like most of those enzyme functions have 20 parameters or so to tweak. And that was already significantly better. So I could generate all those gradient functions which we needed. placed them into an archive, and then I just restarted the whole compilation process. Now that we have a magic archive with all of our gradient functions, we can just link it together, and we are basically done. Except that this doesn't really suit the Rust compilation process. Rust, unlike C++, does not have a stable ABI, so the Rust compiler is allowed to change and adjust the ABI of a few functions on each and every single recompilation. We have 2 compilation processes here, so that's already not really working and limits us to the C types, which is not going to adjust. The issue is not even working then. There are some cases like float values, which the Rust compiler is going to group together. So even if you start with a function taking 2 floats, well, you end up with a function taking 1 double. There are more cases like a function returning a single float is going to be adjusted by the Rust compiler. So instead of having a return value, you now have an input value, which is going to be updated based on the return. You see, it's better, but I just ended up writing more and more LVMIR wrappers that didn't really scale well. And then again, it's kind of hard to sell an AD tool for Rust, which is only supporting C types. So we kind of dropped that, as you can imagine, pretty easy. And well, we ended up, after dropping the cargo build tool, instead we now modify the Rust compiler itself. And that's the place where Lawrence is going to take over and present our current approach on how we achieved that.
So we basically started last month modifying, getting serious about modifying the Rust compiler. So I will first give an overview of the front end, because that's like the starting point. So just a short example, you have like a structure which is parametric at compile time over some number, has some, I don't know, coefficients, and you have some function which you want to, primary function you want to generate the joint function. We now want to add like a new block into this impl, a new function to this impl block. We would do it. This is our current approach. So this is basically called an attribute macro. Everything between the brackets above the function is describing the differentiation rules. So the first one would be our primal function. Then we have the mode we're in and the return activity, and the other, this before the self, which is our self parameter, is an inline attribute, and this basically duplicates it into a second. This self is syntactic sugar for our structure, which then contains our shadow. If you would try to implement this into the Rust compiler directly, it doesn't work, because this is not valid AST, because you don't have a body for your function. So you need to implement a procedural macro before, which basically takes this and transform it into a valid AST, because we don't want to change the syntax of the Rust language. Right, and we did this, right? So a procedural macro basically can take any tokens, which basically any sequence of characters, and produce another sequence of characters, and have this before the compilation process. So you can, for example, also embed Lisp into your Rust code if you want. But it's very useful for configuration, and we also used it here. So after we generate our function, now basically everything happening either before monomorphization, during, or after, at some point in your compilation process, the backend asks for, give us please all concrete functions we have. Before this happens, we have to make sure that our primers are not modified, so we have to disable like ABI optimization, inlining for those functions, and also dead code elimination. So because our primer is not called, because the joint is not directly connected to the primal. So in Rust, those are the different intermediate representation. Like HIR has some desugaring, is concreter. MIR is more like a control flow intermediate representation, where you, for example, only have one kind of control point, a loop. In HIR, you have any kind of loops. So if you would want to write a pass, for example, for Rust, you would do it in MIR, very similar to LLVMIR. So at this point, you basically have to need a query to ask at the front end every time is this function an auditive function, and then we inserted special rules for them. After we've done this, doing monomorphization, we have all concrete functions. We're just collecting them all, building our type trees. They are intermediate type trees because we don't have LLVM context yet, and we're using like collecting all the function symbols. And then after monomorphization, we're collecting from all the different crates, because a compile unit in Rust is one crate instead of one file, collecting them into one big list basically, and then issuing the calls to enzyme and replacing the function in question. Right, and now just some demos. So what's actually supported right now, so you can annotate the primal function like this. You can annotate the adjoint function. This would, for example, if you have like interior mutability, so you can't estimate your mutability based on the reference, you would do this, or if you have like multiple diff roots, of course. Right, and you can either write those parameter activities either inline or above the function. In terms of supported types, so we basically support all Rust types right now, or primitive Rust types at least. So arrays, vectors, slices, boxes, what you want, interactions, also structures. What we don't support yet are v-tables, so they are also like dynamic traits, which have v-tables, but they're more explicit compared to C++. And we don't support tagged unions, so basically enums unions yet. Right, so that would be one example which is already working. So it's a 2D Rosenbrock function in forward mode. That works. That doesn't work. We're trying to figure out why it doesn't work. So there, it's connected to the collect. So basically, you're creating like an iterator. Then you're changing your elements and collecting into a list. But we don't know yet. We have to debug more. Right, and if you want to reproduce this, you can find the README at the GitHub repository. These are basically the steps. Right, and should we do a live demo? Check. So that would be Rosenbrock. So we're creating for the first input parameter and then for the second one, and then comparing them to the result we're expecting. And this is basically how you run it. So here you're hooking up your special compiler. This is our enzyme compiler. And we want to run this example. And yeah, it's already pre-compiled. So it runs instantly. Okay. So we're now coming to the Outlook, and manually speaking more.
Yes. So, well, I mean, as you see, quite a few examples are already working, but of course, there's more which we can ask for. So the first one is we definitely need more test cases, more test users. It would obviously be nice if we can guarantee that all of the typical use cases are working out of the box. We probably also need to add some documentation related to that. Well, beside of Rust CodeGen LLVM, which was the one which we modified by now, it would also be nice if we support Rust C CodeGen NVVM, which is basically another project which tries to replace the backend from Rust C, since it's kind of generic over those backends, and is able to support CUDA, so NVIDIA GPUs. Enzyme itself is able to support CUDA, so it hopefully isn't too much of a difference, especially since this NVVM backend is already quite similar to the LVVM one. We are in contact, so we hopefully will be able to have some basic demos at some point. There are some more things. Well, besides of the LLVM and the NVVM CodeGen, there's a GCC CodeGen, there's a CraneLift CodeGen, and there are some SPIR-V related ones. It would obviously be nice if we have some fallback, probably on Rust MIR level, but that basically means writing a whole new AD tool for Rust MIR. So not sure if I want to promise that will ever happen, but it would be nice. The other ones, right now, what we do in case of some errors, we just throw the whole LVMIR code of that function, which is offending enzyme, at the user. Unfortunately, most Rust users don't know too much about LVMIR, so we probably want to improve on that. But I mean, that's what we already discussed in an earlier presentation here. So we need to help our users a bit more on that. The build performance for large projects should not suffer too much when using AD. on the C++ side, that was sometimes an issue. On the Julia side, they are apparently already quite well. And I think we can also be quite good at the Rust side, because we have all the type informations already available. So the slow part of Enzyme, the type analysis, should be able to, well, if we pass it forward, at least get some improvements on that. Oh.
You have to touch the keyboard.
Oh, okay.
No.
I think
it's
it's
charged.
Oh.
Oh.
That is kind of bad. Well. Yeah, but I mean,
We can also take questions now.
yeah, it was our last slide.
No, there's one important other point. So
Yes.
we had also discussion about safety rules for Rust. Or we can just wait until the slide. But there's on the other side. It's
This gives power too. So. No, you need this for the HDMI. I'll plug it here.
all right.
Now you have power and HDMI in the center.
Shall I talk about our safety issues, or shall we wait a minute?
Yeah, you can keep talking.
Okay. Yeah. So one of the issues which we have about the safety, unlike C++, Rust has some pretty strict rules about what operations are allowed usually and what are not. Those usually require unsafe to get to the same level of control like C or C++. And there are a lot of configuration options for Enzyme, and we are not sure if all of them are allowed under safe Rust. The issue with that is if some of them are not, that would effectively mean all the generated functions which we are going to generate would would require an unsafe tag in order to be sound Rust code. That's not really nice for users to use, because then they have to also mark their whole code block as unsafe in order to be allowed to call unsafe functions which we generated. So if we can avoid that by any means, it is definitely preferable. One of these issues is, as an example, if we have a duplicated vector, or like a slice which is a fat pointer to a vector, well, what happens if we generate a function that takes input which we call with an input vector of length 10, and we provide it with a shadow of length 5. Now we have only 5 elements of the shadow, which are obviously not enough to be updated, so we might just get a seg fault using Enzyme. That's not really allowed to happen in safe Rust. Safe Rust is going to do bound checking and so on, so it's going to be a Rust panic call, and that's, well, on a higher level than a operating system seg fault. So can we add some extra assertions on that? Can Enzyme kind of recognize that early enough, or do we really need to mark our functions as unsafe? There are some more examples, I think, which we skipped.
So you basically have to make sure that the structure of your input and output are the same. You can do that for special cases, but not in general in Rust.
Yeah. Here's a similar one where we use an enum. Basically, depending on the type of our enum, we have 2 different functions under the same name. So what happens if we have, well, one enum kind is, say, float in our case, as our primal, and as a shadow we pass a list, which is basically a vector. Are we able to catch that? Are we just going to seg fault? What is going to happen here? And well, that needs definitely some more test coverage and safety assertions.
Is we need to
I can pass mine.
Okay. Let's thank the speakers first. And now we can take questions.
So is the kind like it is matching on it, right? It is specializing on it, right?
Yes.
So
the size of kind is the largest variant, and it's just interpreting.
yeah, so I'm thinking about this because what my instinctual answer would have been is the safety or unsafetiness of the reverse code is determined by the primal code it is synthesized from.
Yes.
And so as an example, but in Julia, we do not allow shadow variables to be of different type. So you can only pass in a shadow that is of the same type. The challenge with that is we do allow you to pass in a different structure. which could be wrong.
And
So we do not verify that the structure of the type is correct.
the type is defined at runtime?
That
It's so based like a branching? Like similar when you're doing pattern matching?
Well, yeah, you can do union splitting on the type, and then you have pattern matching. Yes.
But since you mentioned the type, from a Rust point of view, those both are from a minimum of type kinds.
And so they have the same size. They have the size of the largest thing,
they have to
and
be the same type, they just
and so yes, the user passing in a shadow of the rung structure
Mm-hmm.
would be undefined behavior and wrong by the user.
exactly.
To add on to that, there's two things, and this is me now at this point sort of like brainstorming things that could be useful. Like I think again, because we consider it undefined behavior internally, if you have structures that are different, because we assume that the shadow is the same overall structure as the primal. So obviously the first best language thing is if you can verify the inner structure before passing it in. It's possible we might be able to do something inside itself as sort of like a validation pass, since like as an example here, what matters is, I'm assuming match eventually goes down to some branch statements. We could, in the forward pass, for certain conditions, and we need to think a little bit more about like when and how we could apply this to not just, you know, load the underlying, is this a float or is this a list of the primal, but also to load that of the shadow and then compare them against each other and yell if you would have gone down a different branch based off of that. The slight bit trickiness there is obviously this sort of check needs to be conditionally defined on what matters, right? Because if it's a comparison, if like, you know, a floating point is greater than a different floating point, then, you know, the shadow should still have a floating point there, but it's probably going to be 0 initialized. So that easily could have a different comparison outcome. So there are certain things that we can imagine doing internally. I need to think more about whether or not and how that makes sense, but I still think it would be nicer if on the language side you could do a validation of that.
So to add on to that, in some ways, right, the path that the reverse mode is taking is determined by the path the forward mode took. And so we're going to record in the forward pass which branch we took and then replay that later on. And so in some ways, what you could think about is to say, well, when we replay, we verify, I do not know, does Rust do runtime erasal of types?
Yes, that's a dynamic type. It can be done if you want.
Okay. Well, in any case, like you could check on the reverse run that when you go into the branch that the structure of the type that you have there is correct.
I mean, if you know it's an enum, you could just compare
especially,
the
yeah.
enum, and then you
Well, the
compare.
problem is comparison is value-based often, not structure-based. That's what makes this tricky.
Yes, yeah. So if you have like an array of different sizes, it's
Yeah,
you can
that is exactly right. You're like, well, I expected that the shadow had 20 elements, and I didn't, and I stored past the array.
But that means we have to define all those functions unsafe. And
Do you have to define them as unsafe?
for special,
Because they're not unsafe themselves.
why?
If a user can use them in an unsafe way, they are unsafe by Rust definition. So if the user can break it with like valid Rust code, then the function itself has to be marked unsafe, because there are some invariants which can't be checked by the compiler, and that's basically happening here. So the user is responsible, and that's unsafe because we don't trust the user.
I do not agree with that. The function that was generated is safe under the condition that the user puts in the correct value. I can call a safe Rust function with wrong data by lying to the Rust compiler, and it will give me the wrong answer.
Yes, but in that
I
case,
can-
you could also segfault, right?
Yeah, of course.
But that's-
I can no. So my point is, I can go through a type hole and cast arbitrary data structure to arbitrary other data structure, even in Rust.
Yes, you can do this, but it should take a lot of effort to do it. It's not
Absolutely,
easy. You can build like such a simple interface and then suddenly segfault when you're doing something wrong. It's using the wrong variant.
So, but that's my point. The function itself is safe. The usage of it is up to the user to determine that it is safe.
Yeah.
You're not saying the function is unsafe.
I
right?
just said that you should define it unsafe because of the user.
No,
They could use it.
no. The usage is unsafe, not the definition of the function itself.
It's true, yeah. No, but
So you have to
one
use
s- one-
to cast those data structures.
Oh yes, and then I created a line.
Right. So the point is, you shouldn't be able to call from safe code and get a seg fault ever. So, like, if there is a function that you can misuse from arguments that you can prepare using safe Rust, like there's no unsafe block, then and that function will misbehave in a memory error kind of way, then the function has to be unsafe.
I agree with you
So-
morally, but not legally.
Now, in this case, to some extent, there's an ability to, like, to lift. Like, you could have a kind that has pairs, so that at the type level you enforce that the pair that's inside has to be of the same variant. And it, like, conceivably we could create an interface like that. It still doesn't deal with the issue of like arrays being of different length, because that is nowhere in the type system that they have different length. It's just a runtime thing that needs to get checked somewhere. The question is where to check it, I guess. I have a question here. This syntax is beautiful, but sometimes you want to differentiate a function with respect to some arguments in one place and with respect to different arguments somewhere else. And using the C interface for enzyme, we can do that. So we can do an enzyme autodiff where some variables are active here, and later on we can do it somewhere else where different variables are active. And can we do anything like that in Rust?
you would annotate your adjoint function. That was basically the idea why we have two syntax. So that's the simple one. And this, like, you would just duplicate this and use different activity for your parameters.
Ah,
And
okay.
it would basically create.
I think even our second marker, which we showed before, would work if you just add multiple lines of those markers, like multiple marker invocations.
So Joseph, in this example, so in this example, you basically presume that if something is not annotated, it's const, and only if you annotate something as dupe, then it's okay. Then you're actually gonna obviously differentiate with respect to that, but you don't require annotations for every single part of the, like, you don't require annotations for all parts of the function call.
Only if they're non-const, then you
Okay.
require annotation. And the syntax is basically duplicate in adjoint means you're taking the first and second as the duplicator, and then it's a simple parser built into the macro at the beginning. They can also do like checking. That's correct.
I have a quick clarification question on that, just to confirm that I understand, and then sort of like a design question out of curiosity. So just to confirm, so suppose you have a function with two arguments, and you want to have one variant where you differentiate with respect to the first argument, and a different time where you differentiate with the second argument. Is it correct that then the way of doing it here is you have, like, you know, cos1, cos2, and then the first one you say active first, and the second one you say active second? Is that correct?
Yes.
Okay. Second related follow-up question to that. So obviously in some of the other APIs, we chose to sort of do this at the call level as opposed to the function level, where you guys choose to do it at the function declaration level. I'm curious why you chose to do that, and then if there's sort of like design reasons why that's better or worse in certain other situations, just because, you know, all these interfaces are, you know, designable and can change. So I'm curious what sort of led you to this particular design.
Because our hope was that when you define it in such a way, then you can also build a macro which defines at the call level, which basically just emits this empty function body and then passes it to enzyme.
I see. So then you could imagine building a second one on top of this that auto-generates
Yes.
that with, like, you know, random, you know, signature afterwards, and then you still have the other interface, but you can also do this
Yeah,
and
and
build.
then you need just one interface in the compiler.
Okay.
It's a bit simpler.
Okay, makes sense. Other questions? Oh, over there. Wait, sorry, did you raise your hand?
So the you have reverse and an active, and active is with respect to the return value, or is right?
Yes, active is return value, right?
Active is return. So you earlier on one of your examples, you had a return value that was annotated, duplicated, no need.
Oh. Okay, let me see.
I think it was in the example.
This one.
Yes.
But that's in reverse.
Oh yeah, I think I had that.
In the burgers, I think.
I think that's an artifact from our forward mode, but I'm not 100% sure. Because on the forward mode there was this question: do you want to have the primary return? Do you have the shadow? Which of the two do you need? I think we probably went forward here. So, like under duplicated.
But in the source code that you ran, you
Yeah.
also had it.
Yeah, we changed this syntax quite a few times, trying to find something nicer. So that's probably a mixture.
My guess here, and I could be wrong under the assumption, is you might have used the same sort of convention as Julia. So for forward mode in Julia, for the sake of the return activity, we chose to overload it to have both the, so you can, as an argument, duplicated and duplicated no need has the convention where the no need variant means don't actually store the original returns on side of it. And since we already have this notion of don't store the returns, then for forward mode, we could, we as a convention inside of the Julia syntax said duplicated no need means don't also return the actual return as well. And I'm guessing that's probably what, yeah, okay.
It was forward mode.
So
Yeah.
we
So this is like
definitely also checked the Julia implementation. Because we felt it would be a bit nicer than C++ interface. Yeah. Maybe we can adjust the names at some point, but yeah.
Cool. Any other questions or comments? Not? Thank the speakers.